Hello and welcome to this course. My name is Thangaraj. I'm a faculty in the Electrical Engineering Department at IIT Madras, and this is Math for Electronics 2, which is a course in the BS Electronic Systems program that the department at IIT Madras offers. So this is the first lecture. It's an introduction. So we'll talk about just a high-level idea on what are the things that we are learning in this course and why we are learning them, and do a sort of a weekly breakup of what you will see in this class. So let's get started. So basically there are a lot of systems that you will come across in electronics and even otherwise across your life as you see things around you in your environment. Many systems have linear relationships between variables that are involved in the system. So here is something that I've shown here. You have some variables from set 1, as I'm calling it, x1 to xn, and then there are these set 2 variables which go from y1 to ym, and the system is somehow maybe these are inputs, these x's are inputs and the y's are outputs, right? That can happen. So in the system it may be taking in these inputs and doing something inside and putting out these outputs. A very common model is to say that the variables in set 2 depend linearly on the variables in set 1. This is a very powerful model and it sort of makes sense quite often, I mean, whenever you want x1 to increase, maybe y1 will also proportionately increase with some constant of proportionality. This happens in many systems. Many physical systems use this assumption to get started with modeling and writing equations. So when it depends linearly, what does that mean? So you will end up having equations of this form. This is what I meant by saying. So let's look at the first equation. It says this y1 variable is actually a linear relationship with x1 to xn. So you have a11 x1 plus a12 x2 plus so on till a1n xn. So this is a very typical system assumption. So all these a11, a12 are some system parameters. They'll have various names depending on what system you're looking at, and then if you scale all these up and add them, you get y1. Similarly, y2 will also be a linear combination of all these, it's linear scales. You scale each variable by some constant, then you add it up, you get y2. So this is a very common situation that you come across all the time, this linear relationship. So now once you have a linear relationship, you can do a lot of interesting things with it. You can ask a lot of questions about it, and maybe one question. Okay, so before I go there to the questions, these aij, I going from 1 to m, right, and then j going from 1 to n, right, m and n, these are usually called coefficients in these kind of systems. These coefficients control the many properties of the system. Say for instance, this a11 might be very large and all these other guys may be small. So then really this y1 depends only on x1 in a strong way. So you can talk about all these kind of relationships between what influences what input influences what output, things like that, once you know what these coefficients are. These coefficients are very important in any system. But what are the kind of questions you may ask here? You may ask, okay, so for instance in this equation, if I know all the set 1 variables, right, if I know x1 to xn, and let's say I know the coefficients also, okay, given the coefficients and given x1 to xn, it's very trivial to find y1 to ym, right? It's just if you know x1 to xn and if you also know these aij's, you just multiply, add, you get the y1 to ym. This is very easy, okay? But notice what this question is asking. What if you only know y1 to ym, okay, and you know the coefficients and you have to find x1 to xn? Okay, so this is sort of like the inverse problem in solving linear equations, right? So you know y1 to ym, you know the coefficients aij, what is x1 to xn? Okay, this is also very common. So the reason is you may want a desired output, you may want a desired output and you may have a certain coefficient and you have to figure out what input will cause that desired output, okay? So this is one kind of problem which is very common, or you may only observe the y1 to ym and these x1 to xn may be hidden variables that you can't observe, but you know what coefficients this system has, then you can go and find what x1 to xn are. So this is very common, occurs all the time. So this kind of linear equations and solving those linear equations is a very important problem whenever you have linear relationships. So this is one type of problem. The other type of question which is very interesting is, you may desire a certain type of system property. So you may say this type of input should go to this type of output, okay, and give me the coefficients, find out coefficients so that I can make sure that this type of inputs go to this type of outputs, and maybe some other type of inputs go to some other type of outputs. Okay, so this is system design. The first one is sort of an analysis question, how to find set 1 given set 2. The system itself is given, you are trying to analyze and try to find something about it. The second one is a design question. How do you design the system coefficients to achieve a certain desired input-output type relationship? Both these questions are very, very important, and both these questions are slightly non-trivial, right? It's not clear what you can do here to make sure that certain output will go to certain type, certain input will go to certain type of output and things like that. We are not really clear on how to get that going. Okay, so these kind of problems are what we will try to solve in this course. So these kind of problems are linear algebraic problems. They are linear and there's algebra involved with these variables to solve them. Okay, so our setting will be, it's typically in the setting where m and n are going to be very large. So if m and n are small, maybe you can think of some ways of doing it. We will start like that, but then eventually we want to make some general statements about situations where m and n are large, and still I want to be able to solve problems like this. Okay, so this is at the heart of linear algebra. So I'm going to show you two examples where these kind of equations arise, and then why these are important in electronic systems, particularly with emphasis to electronic systems. I'll give examples. Linear algebra has applications in every branch of engineering you can imagine, and every branch of science you can imagine. It's all over the place in science and engineering. However, since this is an electronic systems program, I'll show you two examples from electronics where such linear relationships arise, and you want to solve and achieve both these answer both these kind of questions. Okay, the first example is circuits. We saw this example long ago when I was motivating linear equations in Math 1. Those of you who did Math 1, you would have seen that. But even otherwise, let's look at this simple circuit here. Okay, this has got like 5 resistors, and there are 2 current sources here. And you can think of these current source values as inputs, right? I1 and I2 are inputs. And then the outputs, maybe typically the output is voltage across a resistor, or current through a resistor. But I'm going to take these 3 node voltages V1, V2, V3 as my outputs. Okay, and maybe I will work with this a little bit. So we know from our rules for solving circuits that this gives you 3 different equations, and these are the equations. These are node equations that I've written down. All these resistors are 1 kilo ohm, etc. So all these hopefully you agree with me that these are the node equations at each of these nodes, and you get these equations and you can massage them, move this around, so you get a linear relationship between V1, V2, V3 and I1, I2, right? So notice how this comes about, and this you can see will happen in every circuit. Okay, in every circuit that you can think of, there will be a linear relation between the current and the inputs and the outputs. Okay, of course, linear circuits will have this. Many circuits are modeled as linear, and this is how you write equations. So this is the essence of circuits, right? So you may want to know, if I want a certain desired V1, V2, V3, what should be the I1, I2? Okay, so that is sort of that is maybe easy here. But supposing I want so I'm giving you an input I1, I2. I want to find what is going to be V1, V2, V3, and that becomes a solving question. Okay, and then finally the coefficients. Where did the coefficients come from? The coefficients came from this circuit, right? You may also want circuit design questions where I want a certain relationship between I1, I2 and V1, V2, V3. What should be the circuit? Okay, so that's a design question, and that is the coefficient design question, right? So what should be the coefficient? That also you may ask. So all these things are valid questions, and they make a lot of sense in the circuit point of view. Okay, so this is circuits. Let's look at a slightly more advanced question. You have not seen these kind of systems before, maybe, or maybe you have. These are discrete time filtering systems. This is very, very common in many electronic systems. You may have a certain signal coming in, and this will be a discrete time signal, as in you've sampled the signal. It could be a sine wave, for instance. Here's an example. It could be a sine wave which you have sampled fast enough, and these samples are x0, x1, x2, etc. Typically, these samples, when you want to filter them, they go through what's called a linear time invariant filter. This is a very, very common assumption. Many systems in electronics follow this principle. And this filter will have certain coefficients, H0, H1 to HL. These are called the taps of the filter. And then there will be an output that comes out, Y0, Y1, etc. So what is the connection between these outputs and these inputs and these filter taps? They are a linear relationship, and this is how the linear relationship goes. There is also this time invariance property which accounts for the shifting. So you can see here that YL is H0 XL plus H1 XL minus 1 plus so on till HL x0, and then YL plus 1 is going to be H0 XL plus 1, H1 XL. You can see that these inputs have shifted by 1 and you get a YL plus 1. So, for YL plus 2, these inputs will shift further by 1, etc., etc. So, this you will see later on in a signals and systems class, you will see these kind of systems. So, notice how the relationship between the output and the input is a simple linear relationship, and both these questions now, both the type of questions that we asked are very, very important now, right? Given the filter coefficients, find out what type of signals will actually go through. Okay, so this is a question you may ask. For instance, if I send sine waves of different frequencies, what will be the output signal? Will some frequencies go through far better, some frequencies will not go through? All these things may happen, right? Depends on the filter coefficients. So, given these coefficients, what will be the input-output relationship? This is an interesting question to ask. Another interesting question is, how do you design these filter coefficients so that only specific frequencies of sine waves will go through? You may ask that question also, and that also needs some sort of a linear algebra analysis of this linear equations, right. So, hopefully I have convinced you that these linear relationships are not very artificial, they occur all the time. All systems are built assuming some sort of linear relationships, and knowing linear relationships, in particular solving both these kind of problems, solving the equation to given the coefficients, finding input, output, etc., and finding coefficients to give you a desired relationship is also a very, very useful problem. Okay. So, that is the motivation. Let us go ahead and see what is going to be the content of this course. Okay. So, linear algebra is going to talk about vectors and matrices, and very, very importantly, a very important operation with vectors called linear combinations. Okay. So, these linear combinations are intricate part of linear equations and their solutions, and from there we will abstract out and study things called vector spaces, and then subspaces, bases, dimension. These are very crucial ideas in linear vector spaces. And then very importantly, we will move on to ideas such as eigenvalues, eigenvectors, and these will help you solve these kind of coefficient design problems and all that. And then inner product, which is also a very important part. The angles between vectors, magnitude, distance between vectors is very important, and this notion of adjoint of matrices and solving least squares problems. So, this is going to be the crux of what we study from a theory point of view, the linear algebra we will look at. Okay. And in case you are wondering where signals are going to come in, we are going to also see Fourier series and its applications. And here we will see it from a linear algebra point of view. We will introduce Fourier series from a linear algebra point of view. We will view these signals that you have been looking at as vectors in a vector space, and we will see that these sinusoids and complex exponentials are actually basis for the signals, and this Fourier series is nothing but expressing the signal vector in a sinusoid basis. And we will look at these operations on signals and talk about their vector space interpretation, and this will give you a very nice idea of how to deal with signals and systems and what is happening to them as they go through multiple systems. Okay, so, this is the content, but how will we be doing it? We are going to take a slightly different approach in this course. If you remember the philosophy from Math 1, we always looked at the small problem, simple problem first, solved it well, and then tried to extend it, complicate it. So, we'll use a very similar approach in this course as well. We'll first talk about the two-dimensional real plane. Okay, so, we'll do only two-dimensional vector space, which is the R2, for instance, the real plane. We'll talk about it in great detail. We'll do all the linear algebra you can do with it in weeks 1 to 3. And then in weeks 4, 5, we'll move from 2 to 3. It's 2 dimensions to 3 dimensions. You might say we're going slow, but I think the basic ideas behind linear algebra are very well present in both these examples. So, you can really get to understand the concepts and how they apply before you look at the more general case. In week 6 and 7, we will start looking at the n-dimensional real vector space. These weeks may not be very strict. I may move them a little bit depending on how the content works around, but eventually we will get to the n-dimensional real vector space, and at that point you will be able to tackle larger size problems, but the intuition that you picked up from R2 and R3 will carry over into Rn as well. And then we will move to the complex n-dimensional vector space, and what is different. I mean, a lot of things are similar between complex and real, but of course there are also something different. We will point out what changes and how they change, etc. Once we do this, we will move to Fourier series. Okay, the first 8 weeks is linear algebra, and the last 4 weeks is Fourier series seen through a linear algebra lens. Okay, I hope you're excited to learn all these topics. I can assure you these topics will go a long way in giving you a very good handle on electronic systems and signals and really understanding what's going on. Okay, thank you very much.